Good morning, everyone, and welcome to Physical Science. Today is actually Wednesday. Typically, we meet live on Mondays, but because of the special circumstance this week, namely the fact that we had the midterm that was actually opened on, it was due yesterday, and I'm glad a lot of you did it and actually did well in it, so that's actually good. I know I sent several messages, but at the end, most of the people actually did take the exam. We said then, the recording for this week, that we're going to have a live session this week and to discuss, among other things, more details actually about the class, about the this week's assignments and this week's actually. Let me switch to student view in here. I'm in the class. To cover a little bit more in depth the concepts that we introduced then in on Monday, and also to do a little bit of practice, a little bit of problems from this week, and we prepare actually for next week and so on and so forth. So you guys received the invitation again, another reminder, and I'm glad that some of you are here, and those who cannot see it, they're required to watch the recording. Okay, watch the recording and take whatever assignments it is. So without further ado, let me look at again the objectives for this week. But before I do that, I probably need to start recording. Am I? Yeah, it's recording. Good. It happened in the past while I was doing the class that I didn't realize I was recording. Anyway, so let me share the screen. And so this is basically the stuff that you guys have seen. So let me open the objectives again for this week. Again, we have quite a few things. One of them is done, the exam. We still have 2 more exams and a final. So those things are big in terms of your assignment. The exam 4 and final, they're going to be basically a week apart, because the last exam is going to be at the end of the last week of instruction, and then the week after that is the finals week. So the final and the exam 4 are going to be separated basically with nothing between them. The final is a comprehensive exam. So it's from week 1 all the way to the last week 17 or 18. I don't remember exactly what number we're supposed to end. And so this is the idea behind it. So exam 1 covered chapters 1 through 4, exam 2 chapters 5 through 9, exam 3, which is not too far from now, is going to cover chapters 10, which we did a week ago, or was it, yeah, last week, and then chapter 11, which part of it we're doing this week and part is next week, and then we still have chapters 12 and 13. So those are the 3 chapters, the 4 chapters altogether that are covered through exam 3, and the rest, of course, for the chemistry is going to be dealt with in exam 4. So this is how the layout of the exams is, okay? There is a homework that is due this Friday, and that is from way back in week 8. So don't forget to take care of that. And we have discussions also. Some of them have been pushed a little bit to allow for the preparation for the exam. So that's why you see that a lot of them are still due, but that's the reason behind it. Discussion from week 11 is still due. And then even a quiz from a previous week, from week 10 last week, is still due actually next week. So don't forget to take care of all of this. And again, there will be reminders from week 12 when we start next week about some of this assignment that are lingering from previous weeks. The review for this week, and again, the objectives in here, and I briefly talked about them in the recording. So hopefully you guys can go through them. So in a nutshell, this is the story. So let me stop sharing the screen and explain basically what these things are, okay? And I know I did a demo for you guys. I hope that you guys had a chance to look at it, where basically I took a cup of water, basically, it did not have water to begin with. I put a nickel in it, and depending on the angle view, and that's what you're going to be doing part of the assignment, is to replicate that experiment on your own, okay? So basically grab a cup that is not transparent, like a coffee cup, okay? And put a coin in it and stand back, okay, at a certain distance, And as you pour a liquid in it, if you don't have a helper in here, you probably need somebody to pour a liquid in it. If not, then what you get to do in this case is mark where you stood, where you cannot see the coin, where you cannot see the coin, and then pour the water in, and then stand exactly where you stood in before, and that way you will see by refraction the coin. So basically the light that is coming off of the coin from the bottom of the cup, instead of going through a straight path, it breaks in the boundary between the water and the air. Okay, and that is a demonstration of the law of refraction. Does everybody understand what the assignment is for this week in terms of the discussion item? Replicate, demo on the law of refraction involving a non-transparent, it has to be non-transparent, it has to be opaque cup in a coin as done in the previous recording. If you're not sure what I did, just watch the recording from this week. In the discussion for this week, there are two recordings. There is the one that I'm talking about, and there is this one that we're going to have it posted in the same location where that recording is. Does everybody understand what we have in task for the few who are here?
Yes.
Very good. So don't forget, post pictures. It would be nice if you can do a video, but pictures would be enough of your setup. Okay, that's the task that we have to do. Very good. So this is what we have to do just to illustrate the point in here of the law of refraction, because the law of reflection is easy. All you have to do is stand in front of the mirror and you will see yourself on the other side of the mirror. That's actually a reflection, because what you're looking at the light as it bounces off of the mirror and comes back to your eye from different points as it reflects on different points in your body. And it actually replicates yourself, giving you the impression that you exist on the other side of the mirror. So that's how basically images are formed. That's part of the objectives of this week, is to understand image formation, okay? So again, this is some of the stuff that we're supposed to be learning, okay? There will be more in-depth actually image formations next time when we meet, actually when we, am I sharing? I'm not sharing, yes, it's fine. I think you have the points in there. Involving not necessarily flat mirror or concave mirrors or convex mirrors, but rather actually lenses like this one. This is a convex lens, okay? This, the lights come from one side, and actually depending on the angle, okay, it's going to bend and focus in one point. All the light that is coming, depending on wherever it's coming, is going to focus on a specific point away from the lens. The distance between the lens and where the light focuses is called the focal point of the lens. This is a symmetrical lens, so if the light happened to come from the other side, it's going to focus on the other side of the lens. So for this lens in here, it's going to have two focal points, one on each side, and they are of the same distance, okay? And obviously, when you were younger, I should say, you're still young, so I shouldn't really say that. You probably played with lenses, and they most of the time come in shapes like this one. I have a lens in here I'm trying to release from its container, okay? And you can focus light with it, okay? When we were young, or at least when I was young, I was doing this, and it's terrible, but admit it, you try to target ants and things like that, and that's a terrible thing to do. Don't do it again, okay? So anyway, it focuses light from the sun, and it can burn, actually. The light is coming from every single direction of the sun, and it's all focused in one point. So the intensity in that point will become so high And that's how actually fires sometimes start in the forest where there is nobody there. All you need is just a piece of glass or even reflecting rocks. Okay, and if they are bent enough, if they are curved enough, they too have a focal point, and they focus the light in a specific point. And if there is a dead grass or dead stuff in there, it could actually start fires. And that's how sometimes fires start, just by natural processes like this one. So that's basically part of the things that we talk about. Again, lenses, they are not always like this. They are not always convex lenses. These are focusing lenses. They sometimes come in different shape, and I don't have that shape with me, where they're actually concave. They're bent in this direction. So it's like this, okay? And those, they spread the light way. So they're diverging lenses. These are converging lenses. The others are the diverging lenses, okay? And sometimes actually what happens is on one side, it's going to be converging, on the other side, it's going to be diverging. So the lens will appear bent on this way and bent on the other side in the other direction. And sometimes they're actually flat actually on one side and either converging or diverging on the other. So when it comes to lens making, it's really a fascinating topic by itself. And if you ever had the chance to go to an eye doctor, the first thing they do usually in eye doctor is to look at your, if let's say, for example, you need glasses because you don't see well like I do, okay, which is no big deal. A lot of people have this issue. Then the doctor, the eye doctor usually, or the examiner, what they do, they mount different lenses on your eye, okay? And they ask you to focus on a specific thing, like text, for example, and tell you, does it look good? Does it not look good? Does it look focused or out of focus, okay? And they start changing. What they do in this case, they're changing actually the thickness of the lens, trying to change the focal point where the light needs to focus, in here or there, okay? So if it's not too bent, it focuses far away. If it is bent too much, then it focuses up close. That is how they determine the strength of the lens that you will need, the corrective lens that you will need. That's one thing. The other thing also, the eye is a complex system where it has already a lens in it. When you look at your eye, I mean, when you look at the eye, inside that dark spot, there is actually the lens, and it's made out of a material that is actually liquid form and like a jelly. And that too has actually a specific index of refraction that is similar to some extent to that of the water, okay? For all practical purposes, you can use it as water, okay? And it has muscles from both top and bottom. And if you look at something very close and you try to focus on it, the lens changes shape, the muscles work, and the eye tires because of those muscles working very hard trying to look at it. But if you look at something far away from you, the eye relaxes. But as you start bringing something from far away, right now I have this, cannot see it, I have it actually very far away from me, but as I bring it closer and closer, without the glasses, it starts to become fuzzy and fuzzy until I lose details on it. But if I put it at a far away distance, I can comfortably even read the text on it and see the difference between the E and the N. This is the letter that I was reading in here. The point being in here is, as you bring it closer, things start to be, so there is a distance with which the eye is comfortable. Eye is actually comfortable at far away distances, okay? But then you have corrective lenses because you might have a person with a short eye or a person with a long eye. A short eye, basically person, the light that is coming to him, or the light that is going through the lens of his eye, does not focus on the retina. It focuses actually on far away behind the retina. So you need to bring corrective lenses to bring the focus from far to just right on the retina, so that the image is sharp. Because the retina is where the sensitive part of the eye is to take the message to the brain and tell you how the image forms. Some of the people actually have a long eye, and the long eye, the image is actually formed before the retina. So in this case, you need to have corrective lenses to push the focus away from where it is toward the retina. So that is basically the distinction. The eye is a very fascinating and complicated system, just as much as the ear is, as a matter of fact. If not, the ear probably is far more complicated because it has moving parts. It involves the drum that moves in and out. The other one does not. Once you have the lenses on, usually you don't have a problem with that. So usually you don't have an issue with the with that. Of course, with age, things deteriorate anyway, and our sight is not good anymore. So we really need converging lens, and we need lenses depending on how far are we far-sighted or nearsighted, and that is where the details comes in. Makes sense for those who are here?
Yes.
Okay, very good. Listen, I know some of you guys are my students, and not necessarily those who are here with me, but those who are watching the recording. You're probably into life sciences, and you have a lot of details on this topic when it comes to the eyes, and probably even you're considering maybe working in optometry. It really relies on the subject of light. So for all of this, all we need are the first two laws we discovered: the law of reflection and the law of refraction. So let me share again the screen. Here are the two laws. When we talk about mirrors, whether a flat mirror, whether a concave mirror, or whether a convex mirror, usually it's the law of reflection. And the law of reflection is simple. All it says is there is an incident light to the mirror, and there is a reflected light from the mirror. The law of reflection says the angle of incidence is equal to the angle of reflection. Easy enough. Provided you can draw the perpendicular to the surface, called the normal, then the incidence is the angle made from the ray that hits it to the normal. And the reflected, in this case, will make an angle. The angle of reflection is the measurement from the ray that is coming out to, again, the normal to the surface. So this is, in a nutshell, how the law of reflection is. When it comes to lenses, though, similar to the experiment, to the demonstrations I did for you guys, and hopefully you guys are going to replicate part of the assignment of this week, it uses the law of refraction. The law of refraction is a little bit more involved. This was known to humans for a long time, okay? As a matter of fact, according to Mr. Feynman, in his famous Feynman lectures, there is actually a 3-volume book. I have it in here. Oops, don't fall. Okay, Feynman lecture. Do I have it back one? Yep, I have it back. Okay. I have the 3 volumes, but actually, if you're interested, I know the topics are a little bit more involved, especially in terms of math. This is for calc-based students usually who go into that one. But there is actually a free version of the book online given by Caltech. If interested, I'll give you the link for it. Or just look for Feynman lectures from Caltech, Pasadena, and then you're going to find the link. Anyway, he states the fact that the Greeks were known for their philosophical and mathematical inquiries more than anything else. However, there are documentations where the law of refraction was actually documented by the Greeks. So they did not necessarily a thought experiment about it, but they actually did an actual measurements. So you have a ray that comes in. Let's say, for example, we take the simple case of water, air, like we did the demonstrations. We have water in a pond, for example, and we have somebody looking at it from outside. If you take a rock, for example, and focus on a rock, because fish moves and sometimes it's very hard to locate it, or at least if you go and try to do measurements, you're not going to be able to find the fish in the same place. But take a rock, for example, sitting in the bottom of a pond, calm pond, calm. okay, not moving, because if it's moving, there is an issue in here of waves that you have to deal with. That's not a big deal, really. But the point in here, you have a rock, and then you have a point of observation. Similar to the point I was telling you earlier, you have to make sure you know your location, and then you experiment with it. As you change location, again, the image where the rock appears changes. As a matter of fact, if you move at a certain distance, you're not going to be able to see the rock. And that is the total reflection point. That is point where the rock is completely disappearing from you, although it's in there. Okay. So again, this is stuff that was documented, and the law is actually involves the trig function. It involves the sine function. Okay. So that is basically, instead of involving their angles themselves directly, it involves their sines. And something that was kind of a property of the material itself called the index of refraction. What the index of refraction turned out to be is just the ratio of how fast light moves in that medium. In air, light moves with practically the speed of light. In water, it moves slower by a factor of 1.33. And that is the index of refraction, actually. Okay. So this is in a nutshell the stuff that is covered in this topic. Okay, I didn't mention the first thing in here, and I know I talked about this before. Actually, I need to talk a little bit about these 2 points, although I mentioned them in the prompt. Okay, historically, light was a puzzle, and it continues to be, as a matter of fact. Historically, people wanted to understand this loss. Again, we are going through the same process again and again. Namely, you do an observation, or you do an experiment, or you do a measurement, and then you would want to understand a model. You would want to put a model to understand what that experiment is telling you. That's the whole thing. If I look at the law of reflection, for example, and if I take a tennis ball, for example, and I throw it against the wall, the tennis ball will bounce back, provided I use the conservation of energy and the conservation of momentum, bounces back according to the same law I was describing in here of the angle of reflection equals to the angle of incidence. So this is perfectly justified. Now, if I throw the same rock, for example, in water, the water slows down the rock, and the ball will cause it to go at an angle. Okay. As a matter of fact, I don't need to do a tennis ball, because tennis ball is going to be a bad example to do on the water. I can use rocks, actually. The rocks, they don't absorb water. So if I throw the rock will slow down to the point that I will see that same refraction. So all we are saying in here is that maybe, or actually, if we do the experiment of reflection instead of doing a tennis ball, because tennis ball is actually a good thing to do with, because it's kind of elastic a little bit. But if we do it with, for example, material that goes back to its original shape, like for example marbles, it's going to be the same experiment, provided they don't break. Let's not hit it too hard enough. Okay, or even with billiards balls. So it's the same thing. It's all of it producing the same experiment, indicating that light is made up of tiny particles. So at that point, when Mr. Newton came up with a theory trying to explain these two phenomena, then the idea is that light is actually a particle. Whatever it is, it's a tiny particle. We don't know what it is, but it's so small, and it's a bunch of them moving in the same line. And as they hit that one, they bounce back. And so this is the idea. The idea is called the corpuscular theory of light. That's how Mr. Newton called it, actually. And that stood for a little bit of time until Mr. Young started experimenting with and actually before him there was some observers in modern day Italy about the light, especially with tiny objects as it goes around them, extremely small objects or extremely small openings. So Mr. Young did the experiment, and he found patterns that form from light going through small slits, I call them, openings. And those patterns only can be explained by a wave behavior of light. So light is not a particle, It's a wave. He did it with a single slit as long as the opening is so small, extremely small, of the order of a fraction of a micrometer. If it is, then you will have patterns that form on the other side where you have fringes that form. Some of them are dark, some of them are bright. When you do these experiments, when Mr. Young was doing it, he made sure he was dealing with the same color, monochromatic light, because if you use white light, it spreads around and different frequencies break apart and you will not be able to study it. Unless, let's say, for example, you have a red light like this. I have another one somewhere. Like this laser source. This is a monochromatic light. As a matter of fact, the frequency of this one should be about, the wavelength of this one should be about 600 or something. And it should say in here somewhere. And I don't have my, where is that? I have another magnifying glass in here. Oh, this is actually this is a converging diverging lens. Okay, so it's not good. Okay. Anyway, the point being in here is that when he sends that light through a slit, it's going to produce patterns unique to waves. Places where there is constructive interference called bright fringes. Places where the wave cancel completely called where destructive interference happens, and those are the dark fringes. And it alternates actually. Dark, bright, dark, bright, dark, bright, and so on and so forth. This can only be explained if light is a wave. If you take the same light and run it through small slits, and depending on how far apart they are from one another, again, you're going to produce patterns unique to waves, constructive and destructive interference. So Mr. Young was faced with the problem that light cannot really be as thought to be a particle, but rather it's a wave. So there was a problem now. How can we explain the law of reflection and the law of refraction using the new found as a matter of fact, he was not only able to say that it's a wave, he was able to measure the wavelength. And because of earlier experiments, we were able to find the speed of light. We were also able to find the frequency. So not only is telling you it's a wave, but it's telling you what its frequency is and what its wavelength is. So that's the thing of Mr. Young. We didn't know then what was waving. We had no idea. This is in the early 1900s. We had no clue what was waving. We know it's a wave though. What was oscillating? That was the problem. That is the question. On the other side, Mr. Maxwell, he was trying to put all of the equations of electricity and magnetism together. And he found the flaw in one of them and he fixed it. In the 1880s, he was able to come up with a group of equations called the Maxwell's equations. And when he solved them, he found that the solution is actually a wave that has the same speed as that of light. So immediately said, okay, maybe what Mr. Young was talking about is this one, that light is an electromagnetic wave. I'm sorry, I did not answer a critical question that I raised, but it's very important. And it's always true that you always have to question that. A new experiment that with Mr. Young that can explain the new phenomena that you see, which is a wave nature, need to also explain the old stuff that was discovered. Otherwise, you have a problem. And for that, Mr. Huygens came up with a principle actually, and he said, okay, let's think that Mr. Young is correct. Okay, that light is a wave. If we think that the wave front as it's moving of that wave, every single point of that wave front becomes a source of a new wave, if you wish. He didn't call it a wave, he called it a wavelet. Source of a new wavelet. And so every point, so if you take point and another point, of course, mathematically points are an infinite number. So regardless of how many I take, I will have to take as many as I need, and each one of them has its own wave. Most of the time it's destructive interference, except where the envelope that circumvents the entire wavelet, that is the new wave front. And he was able to reconstruct the wavefronts as they're moving using this principle called Huygens principle. So every point on the wavefront becomes a source of new wavelets, and these wavelets travel in every single direction. And as they do, wherever you are in space now, just take the envelope that covers the entire wavelets, which is an infinite number of them, and that envelope becomes a new wavefront. So you can construct the motion of the waves this way. If you take that principle of Huygens, you can actually reproduce the law of reflection and the law of refraction using Huygens principle. So he was able to, Mr. Young came up with a new idea based on observations. He was forced, he didn't have any choice. And Mr. Huygens fixed this issue for us. So now we have no problem. Everything looks good. Everything is fine, okay? So light is actually a wave. The suspicion that light was a wave is actually traces back to before Mr. Young, but Mr. Young put the nail on the coffin, saying that this is the wavelength and this is the so now basically we have abandoned Mr. Newton's idea that light is a particle anymore. We don't need it because now we have light is a wave and we are all happy and we can explain things that Mr. Newton was able to explain. And then we can explain more than that, what Mr. Young has found. Everything looks good until, like I said, the time when Mr. Maxwell put everything together. At that point, we answered another critical piece of the puzzle, and that is what was waving, because the solution to his equations in free space was electric field creating a magnetic field, creating an electric field, creating a magnetic field, and in the cycle. And that's what was waving. So it's really the electric field going up and down, the magnetic field going left and right, and both of them moving in the same direction as they're doing this creation. And basically, they are creating one another, basically. And in the cycle, that is what was waving. So everything looks beautiful. Everything up to that time, everything fits everywhere. So we know what was waving. We can find what the wavelength is. We can explain reflection. We can explain all of optics, actually, not just reflection and refraction. So we're in great shape. Now, he was able to unify electricity and magnetism and optics and put them all in the same place. Everything looks beautiful. Except there was experiments again, and I mentioned them in the previous recording, involving the photoelectric effect. What the photoelectric effect was, basically, if you have a metal and you shine light on it, if light has specific frequency higher than a certain minimum frequency, charges start to get out, and those charges actually can capture them, and they form an electrical circuit. This is the principle behind the photocells that some people have on their houses. So this is the photoelectric effect. That was a puzzle. That was a problem. The only way to explain that was Mr. Einstein actually came up and borrowed an idea that Mr. Planck has introduced to save the day from another phenomenon called the ultraviolet catastrophe. And he took that idea and he said, you know what? Light is actually a particle after all. And he called the particles photons. And now the photoelectric effect can be explained. Later on, in the 1920s, there were other experiments involving light with extreme high frequency, and those experiments involved the scattering of those high moving, basically high frequency, high frequency lights, namely the gamma rays, and they scatter as they hit electrons. And that scattering can only be explained if they are actually particles also. This is called the Compton scattering. So now, what is it? So that's the question. What is light? Is it really a wave, like Mr. Maxwell basically put it all together in one beautiful theory that explains all the work of Mr. Young, the laws of reflection, refraction, and the optics and everything else, which is clearly a wave? Or is it a particle like Mr. Einstein has suggested, explaining the phenomenon of photoelectric effect and Compton scattering and other phenomenon? And the answer to the question, of course, is light is both. These are irreconcilable. You cannot reconcile these two ideas together. Either a wave, which is spread in space and has no definite location, or a particle that has a definite location in space. But those two are completely different antagonist ideas, but that's light what it is. It's basically these two completely two things that don't seem to fit together. But that's how light behaves. Sometimes it behaves like a wave, sometimes behaves like a particle, depending on the experiment. Right. So that's in a nutshell where we are. So this is historically. So the answer to the question is, what is waving? It's actually the electric field and the magnetic field. Transparent materials and non-transparent materials. So let me go a little bit into so this is the quiz. This is the quiz. This is the exam that you guys had a chance to go through. And this is what I was talking about in here, the oscillation of the electric field, magnetic field. And as they do, we have all of this moving in one direction, basically, and moving with the speed of light. We talked about the spectrum in here. So light is a special circumstance of all of this big spectrum that includes the low frequency, long wavelength, and the high frequency, short wavelength. The law of reflection, the basically materials absorb and transmit light depending on their properties and how light basically interacts. Every material has what is known as a, even the absorbing materials have a penetration depth, basically, of how far light can go in, depending on the properties of the materials. This is a mosquito in here, okay? The point in here is that some other materials, they transmit it all the way through. Like, for example, glass transmits most of the time the radiation in here. For the most part, the infrared is actually absorbed for the most part versus any other frequency, versus even the UV. But that's part of the properties that, these are the two laws I mentioned, and that's the image formations. So let me get into the applications. We spent quite a bit of time on the review. Any questions so far before I get into the problems?
No.
Okay, very good. So let me share with you. I know the problems are not posted in a sense what problems are, but they're actually going to be available early next week for you guys for the week 12. And if you want to jump ahead, the statement is not complete. Obviously, you can tell from the problems in here, from 38 to 44 on page 295. So from the book, it's page 295, problems from 38 to 44, okay? So these are the problems we will be doing. And so let me deal a little bit with each and every one of those problems quickly. And if I go too fast, slow me down. Tell me, hey, can you explain that point again, please? And this is the same thing for you guys who are watching this recording later on. And if you think that this went too fast, you can always come back to a specific problem and ask about it, and we can talk about that problem again, either in one-to-one communications, or if it's something that can benefit everybody else, and I will share it with everybody so that everybody will see exactly what these problems are. So let me take my notes in here, and let me go to the physical science, and no, I don't need to add anything. I can just share that screen with you guys. But I need to move those assignments because I need to see them while I'm working on them. So let me move this to the other screen. And hopefully you guys have the book. And if you have the book ready, you can start. And again, I know one of you guys or some of you guys, sometimes you rely on me basically talking and doing things and not doing them. That is not how it's supposed to work. While I'm doing this, even if you're watching this recorded, you need to pick up a piece of paper and a pen or a pencil and start doing the things I'm doing. That is the only way how this thing will work. This is not a spectator sport, as someone said before. You have to be fully engaged doing these things, otherwise you will never be able to do them on your own, and you will have difficulty later on doing them. I'm talking a little bit to give you time so that you can go and grab a piece of paper and start doing this, okay? These problems. So the first one, this is what from last discussion, I guess. So again, Problem 38. It says electrons on a radio broadcasting tower are forced to oscillate up and down an antenna 500 and so this is 38 by the way, 535,000 times per second. Show that the wavelength of the radio is 561 meters, half a kilometer. This is a typical radio wave signal. Okay, so what does that mean? It oscillates 535. That means it goes back and forth, the charge, back and forth, back and forth, back and forth, 535,000 times per second in 1 second. This is actually the frequency itself. Frequency sometimes in other literature is used the Greek letter nu, okay? In this textbook, I think we use the letter F for it. So this is the frequency that is given to us. So how often it goes back and forth? That means in one cycle, in one cycle, going up and down, going up and come back, is going to take 1/535,000 times. This is how many seconds it's going to take. Fraction of a fraction of a fraction, 535 times, many times of a second, in order for it to do 500 in 1 second. So that's basically what this is saying. So this is actually a period. And we don't need the period for this one in here. We need just the frequency. Remember the dispersion law that I mentioned? Lambda times f is equal to the speed of light, and the speed of light is 3 × 10⁸ meter per second. This is a good number to know. The frequency is not usually said in 1/second, but they call it in hertz. Hertz is exactly 1/second. So the frequency is 535 hertz, 535,000 hertz. Okay, that's the frequency, 535,000 hertz. So if they tell you it goes this many times in 1 second, that's what they meant with it. They mean the frequency. So from here, it's clear cut that you have to find lambda. All you have to do to find lambda is divide 3 × 10⁸ divided by 535,000. This is in meter per second, and this is in hertz. And hertz is actually 1/second. If you like, the second cancel the second, and the answer is going to be in meters. Your task today is to complete all of these problems, so finish it. I'm not going to do the calculation. I'm going to rely on you doing the actual calculation. This is second item of the discussion today, is complete all of these calculations. Here is what the problem is saying. The problem is saying that show that it is equal to this number. Is it 561? That's the question. 3 × 10⁸ divided by 535,000. That is what you're supposed to do with this problem. Make sense? Sounds good?
Yes.
Okay, very good. So let's do 39. So this is the second task, is to complete all of the calculations, because I'm not going to do them. Consider, so this is 39 now. By the way, the last problem we're probably going to defer till Monday, okay? Because the last problem, problem 44, involves the second part of this class, which is the polarization, okay? So we're not going to talk about that until that day. Anyway, 39, consider a pulse of laser light that is aimed at the moon and bounces back to Earth. So you have the Earth in here, and you have the moon in here. Okay, so you have a laser beam, you send it up, and it comes back. Okay, the distance between the Earth and the moon, this distance from here to here, is 3.84 10⁸ meters. It's basically 384,000 kilometers. Okay, 384,000 is 384 million meters. That's exactly what it is, 3.84 10 to the power 8 meters. Show that the round trip takes a time of 2.56. We know the speed of light. Light will travel 1 and comes back. So it travels twice this many. When it goes up, it travels 384,000 kilometers. When it comes down, it travels another 384,000 kilometers. So the speed is equal to the distance covered divided by the time. From here, we can find the time to being distance divided by the speed. Except the distance is not 384,000, it's actually twice as much. That's all. So the time then is going to be 2 times 3.84 10 to the power 8 divided by the speed of light, and I already written it up in there. It's 3 times 10 to the power 8. To make life easy on yourself, cancel that 10 to the power 8 by 10 to the power 8 because it's both of them 100 million anyway. So you can cancel 100 million and 100 million, and you will be left with doing 2 times 3.84 and divide that by 3. Well, they're saying show that this is 2.56 seconds. That this time, that's what you're supposed to do. Is it equal to 2.5 seconds? That is what you need to check. I didn't do the calculation, but you have to check it yourself because I really need to do 2 times 3.84 and divide that by 3. Is it? That's where the question mark in here. Is it 2.586? Okay. That's 38. I mean 39. 40 now. It says the nearest star to the sun is Alpha Centauri, and Alpha Centauri is at a distance d equals to 4.2 times 10 to the power 16 meters. This is Alpha Centauri. It's usually like this. Okay. Show that if we were to receive a message from this star today, it would have taken this 4.4 years. So this is what you got to do again. It's very easy. All we have to do is the distance is equal to the speed times time. It's the same formula in here. So we're going to find this, the time is equal to the distance divided by the speed of light. Here is so this is a light. Somebody send you a signal, they have to send it to the light. They're not going to send you a phone call because phone doesn't, they're not going to scream from there. You're not going to hear them because sound is not going to be traveling through vacuum, but light does. So the only way that you're going to receive a message from them is through a light signal. So they're going to send you, like, for example, Morse code or something, okay? Or a signal that you can take it and, like, for example, in our your cell phone right now uses actually electromagnetic waves to communicate between the tower and itself, and between the tower and the tower it communicates also with the electromagnetic waves. So that's basically the whole thing with light. So the time is the distance. They said specifically it's 4.2 times 10 to the power 16 meters, and the light travels 3 times 10 to the power 8 meter per second. Okay, again, 10 to the power 8 and 10 to the power 16. I will have 16 minus 8, that's 8. I will be left with this 4 number. Of course, the meter cancels the meter. I will be left with 4.2 divided by 3, which is what? 4.3 divided, it's 4.2, is it 1.4? Probably it's 1.4, yes. This you don't really need a calculator for it because 12 times plus 12, that's 24 plus another. No, actually, what am I talking about? No, 14 plus 14, that's 28, and another 14 is 42. So yeah, that's correct. Times 10 to the power 8 seconds. So that is the answer, which is 1.4 times 10 to the power 8 seconds. But that's not what we need, actually. They want you to show it takes 4.4 years. So the question for you is this 4.4 years. There are 2 ways of doing this. Either you take this 4.4 years, every year has 365 days, and every day is 24 hours, and every hour is 60 minutes, and every minute is 60 seconds. So you multiply this by that, by this, by this, by this, and the answer should be 1.4 10 to the power 18 seconds. Or, so that's option 1. Multiply this whole thing, and it should be this number. Or you take 1.4 times 10 to the power 8, which is 140 million. This is 140 million seconds. That's what this number is. And divided by, again, 1 second is a 60th of a minute, which is a 60th of an hour, which is a 24th of a day, which is 365th of a year. So if you do that, you have the answer in years. Okay? Is this number equal to 4.4 years? You have 2 ways of doing this, okay? And it's up to you. Man, I have a mosquito in here. I really need to. I opened the window earlier to get some of these things out and actually clean stuff, and now it's everywhere. Anyway, so does this make sense or not? For those who are live in here, for those who are not, you guys are out of luck. You're going to ask the question in the inbox or email, and I will answer that to you guys too. Make sense?
Yeah.
Okay, very good. Man. So 41. It says a blue-green light. Sometimes it's referred to as a blue only, because depending on how your perception of colors is, has a frequency of 6 times 10 to the power 14 hertz. So this is the frequency, okay? Using the relationship C equal to lambda F, or F lambda, lambda F, show that its wavelength is that many meters. Oh, no. There is a typo in the, I'm gonna fix that right now because it's not correct, okay? Let me edit this. I mean, it's correct in the book. It's correct in the book, by the way. But in here, I made a typo. So while I'm there, let me fix this. This typo in here, because it cannot be correct. I know that. And let me fix this problem in here from 38 to 44. Let me see. I'm glad I'm doing this live with you guys so that these things are fixed. So it says, show that the wavelength is 5 times 10 to the negative 7 meters. 500 nanometers, that is. So this is basically what we're supposed to do now. We have C, which is 3 times 10 to the power 8 meter per second. We don't know what lambda is, that's the question. We have the frequency, which is 6 times 10 to the power 14 hertz. Okay, from here we can find lambda equals to 3 times 10 to the power 8 divided by 6 times 10 to the power 14 hertz. So this is meter per second, and a hertz is 1/2. The second cancels the second, and the answer is going to be in meters. 14 and 8. 8 minus 14 is -6. Okay, so I have 3/6 times 10 to the -6 meters. But what is 3/6? That's 1/2. So the answer is 0.5 times 10 to the -6 meters. 0.5, by the way, in scientific notations is not acceptable in here. So I have to move the decimal point to this side and add this power or subtract this power, another 1. So it's going to be the correct answer in here. So this is your lucky. I did the whole thing because I don't need a calculator for this one. So this one, you really don't need to do it. So 5 times 10 to the -7 meters. Sometimes this 10 to the -7 and -6 actually is not sometimes, it's always called a micrometer. So the answer is actually 0.5 micrometer. 10 to the -7, that's another way. That's what you're supposed to do. So this problem is answered for you. So you really don't need to do anything to it other than noting the fact that 5 to the 10 to the -7 meters is 100th of, or 100 times more than a nanometer. because a nanometer is 10 to the negative 9 meters. A micrometer, like the one I wrote in here, is 10 to the negative 6 meters. So the 10 to the negative 6 meters is the same thing as a micrometer. So the wavelength is half a micrometer. Or in nanometers, I'm going to make this one 10 to the negative 9, so I have to multiply by 100. So the answer will be 500 nanometers. The reason why I'm saying this is because this is a well-known number. Usually people, when they check the wavelength, they refer to them in nanometers. So 500 nanometers is the blue color that they are talking about in here. So this is a well-known number. As a matter of fact, I know some of you are sitting in my astronomy class, and they know we have something similar in astronomy class, where we have something called the Wind Displacement Law, which is actually here also, and to some extent we're going to be talking about. We talked about it when we did the black body radiation, but we're going to talk about it some other time too. And that formula, let me tell you what that formula is, because we're talking about it, especially those who are sitting in astronomy, they are very familiar with that thing is. So Wind's displacement law has this formula in it, 2.9 10 to the power 6. Divided by, I'm sorry, not that. This is T, the temperature, T for temperature. And they have the lambda, the maximum wavelength for the distribution. This has to be in nanometers. That's why I'm saying converting it in nanometers, because most of the time we really need it in nanometers. We don't use meters for this purpose. And of course, the units in here are in Kelvin, because the temperature has to be Kelvin, in nanometers too. So this is called the it's called Wien's displacement law. Again, for those sitting in astronomy, they know exactly what we're dealing with this one is. If not, we probably are going to, we need it actually for the black body radiation, but because we did that before this topic, so it did not really make sense a lot, honestly, but now it should too for us. And we're going to come back to this topic down the road. Anyway, law. So this is problem 41 is fully, I mean, we investigated from top to bottom. Oh, we still didn't need to answer another part of the problem. How larger is it this compared to the size of an atom? The size of an atom is actually about 10 to the negative 10 meters. That's how big the atom is. And this wavelength is 5 times 10 to the negative 7. So the wavelength of the blue light is from here to here. No. What is the wavelength? Starts and come back. Yeah, this is the wavelength. Okay, this is lambda. This is 5 times 10 to the negative 7. If I do the ratio of this over that, the size of the atom, obviously 10 to the negative 7 minus 7 plus 10, that is positive 3. So the answer is 5,000 times bigger than the size of the atom. So if you take an atom from side to side, I'm not talking about if I take the diameter, this, you will need 5,000 atoms lined up one next to the other to make a wavelength of blue. Why is this important? In other words, can I use a microscope? Microscopes are powered with regular light, okay? That has this typical wavelength. Can I use a microscope to see the atom? And the answer is no, because the wavelength of light is too big. It cannot give you the details of what the atom look like. It's too tiny for it. The size of the atom is smaller, a lot smaller than a typical wavelength. If I want to see the details of the atom, I need to explore it with a wavelength small enough so that it gives me the details of that atom. And the wavelength for regular light is too big compared to the size of the atom. So I will not be able to see an atom under a microscope. But an electron microscope can. Okay, an electron microscope uses electrons, and the wavelength of an electron is too small. So an electron microscope can give me some fuzzy picture. So the pictures that you see there for the atoms out there, and you can Google it, they are not produced by regular light, because regular light is too big compared to the 5,000 times bigger. That's the blue light. Blue light, by the way, is short. Okay. If you're talking about red light, it's 700 nanometers, so it's 7,000 bigger. We're talking about blue light, which is short to begin with, and yet it's 5,000 times bigger than a typical atom. So it's not useful. So I think with this problem, we killed it. I don't think that we can talk about this problem anymore. How we're doing on time? We still have a few more minutes. Okay. The spider hangs by a strand. Now we're doing optics a little bit. Problem 42 now. Okay. So you have a spider in here. So here is my rendition of a spider. Here is a mirror. And here is you. Okay. It says a spider hangs by a thread. Okay. It's convenient now we're in Halloween season. Okay. Okay. Hangs by a thread at an eye level 30 centimeters from a mirror. Here is this distance is 30 centimeters in front of the mirror. Okay. And it's 65. You on here, this distance is 65 centimeters. The question is, show that the distance between your eye and the image is 125 centimeters or 1 meter and 25 centimeters. So here is where the image is going to form. It's going to form 30 centimeters away. So this is what the spider would look like from the mirror. Because again, the flat mirror, that's the one we're talking about in here, has a magnification of 1. That means the distance between this point and this point is the same. So all you have to do in here is add 65, because you're looking at the image, to 30 to 30, and the answer is 1.25 meters. So I need you to check this addition in here for me. This should be straightforward. If it's wrong, please let me know. If it doesn't check, please let me know. Okay. Problem 43. When you walk toward the mirror, you see your image approaching you. Here is the mirror again. And here is you. But this time you're not sitting still, you're actually moving toward the mirror. And you're moving with a speed of 2 meters per second. How fast do you and your image approach one another? Here is the thing. You're moving toward the mirror by 2 meters per second. The image also is approaching the mirror, and the image, you and the image should approach one another with this relative velocity. Basically, you have 2 cars sitting still. One of them is sitting still, and the other one is 50 miles per hour. Obviously, you're sitting in the car, you're looking at the other car coming at 50 miles per hour. But if you're moving toward the car with 50 miles per hour, and the car is coming with 50 miles per hour, that's going to be a big collision. Hopefully, you don't do that. But the point being in here, you're going to be approaching one another with 100 kilometers per hour, 100 miles per hour. Okay, because it adds up. Same thing in here. So it's going to be the relative velocity from your vantage point. This one would be. Okay, very good. So here is the deal. We did all of the. I didn't do 44 in purpose, and that is because we are still did not finish the materials for this chapter. So if you guys have any questions, please do not hesitate. Send them. I have my regular office hours, and I can meet with you even outside of the regular office hours whenever you want to make sure that you are at ease with all of these problems. And this homework is still not due yet. So I still have plenty of time for you guys to finish it. You still have about 3 weeks or something. Almost 3 weeks, not quite so. Okay. You have about maybe almost 20 days. No. Let me check exactly when it's due so that I don't give you the wrong information. It's due November 13th. And today is October 27. So you have 13 plus 4, 17 days. So we still have plenty of things. So here is the tasks for the day. Again, just a reminder, quick reminder. The first one is to do the demo that I did with the refraction. So hopefully you guys can reproduce that and send your pictures. And the second is to make sure that I didn't make any mistake in here, and you replicate the numbers and make sure you fix the answers and the answers are correct. And if there is a mistake, you let me know about it and you post that in the discussion. Sounds good.
So for the discussion number 2, do we just answer if there's any errors or if it's correct?
No. Actually, go through the problem. 38, here's the answer. I know that you're going to be doing the homework again, but because I just did the calculations, all you have to do is just finish those steps.
So we just put the answer for discussion number 2.
Yeah. If there is a mistake, I need to know about it. If there is something that you discover is wrong, I really need to know about it. I don't claim knowing it all. And that's why I really need your help to make sure that I don't make mistakes, and everybody needs to benefit from that. So if there is a mistake, I need you to know about it. If not, you're still required to do the calculations and finish them. Sounds good?
Can you repeat that again? Because I don't know if that's my Wi-Fi, but it goes.
Okay. Yeah, sometimes it's actually not your Wi-Fi. It's the problem in here too. Okay. For the second task, complete the calculations. If you discover a mistake, let me know. Not, you are still required to post the calculations and the discussion. Sounds good, Sabine?
Yeah, and for the demo, is it on week 11, the video?
Yeah, it's the week 11. The previous recording, it's actually on the same. This week has 2 videos. The first one, I did it kind of quickly because of the fact that we had the exam. So actually at the beginning of the video itself, I did the demo. Sounds good?
Yes.
Okay. So hopefully I'll see you guys next week. And if you have any questions, do not hesitate to send them. And I'll talk to you guys. Let me stop the recording.